So carrying on with the idea of usefulness and realisticness in the theory and the limiting reagent part of this, we're going to move on and talk about percent yield. So in chemical reactions, the amount of products one should get based on like the stoichiometry that you just did doesn't always actually result in the products that you get in the lab or real world chemistry. So we could talk about what you should get as calculated or theoretical. Or calculated. And you could talk about the actual amount or the experimental amount. So if you think about the pancakes recipe, maybe the limiting reagent one, maybe you had a limit on how many pancakes you could make, but you made them a little bigger than you should, so you didn't make as many pancakes. So what we're doing with percent yield is taking reality and measuring that against the ideal situation. And so it's basically what you get out of what you should have got times 100, kind of like a test score. So this is percent yield and is really just a tie into that idea of stoichiometry. So stoichiometry allows us to calculate the theoretical yield. The actual yield is what you get in the lab or experimentally. So in solving the percent yield problems, it kind of rolls everything in together. So you're going to have to determine the limiting reagent to calculate the theoretical yield and then plug into that percent yield to figure out how well you did. So here we have our first example. So we're back to this example with nitrogen gas reacting with an excess of hydrogen gas. So I don't think this one's going to be a limiting reagent. And it says, what is the percent yield if 55 grams of ammonia are produced? So let's sort our information. We've got 50 grams of nitrogen. We've got an excess of this, so we can pretty much ignore it. And we do have a mass of ammonia, but this is the experimental or actual. So what we need to do is calculate the theoretical yield and then compare that to the experimental. So always with this, we're going to start with what we know. We want to move over here to figure out how many grams should we theoretically produce. So, whoops, and I'll be complete with my unit factors so I don't make a mistake. N2. I'd have to convert to mass of nitrogen gas, so N2 is just 2 times the 14.01. So a total of 28.02 grams per mole. So 1 mole of nitrogen gas would be 28.02 grams. So that'll tell us how many moles of that we have. And we know that we're moving over to our product. So we don't care about moles of nitrogen gas. What we do care about is moles of our product, which is the ammonia. The numbers for these come from the balanced chemical equation. That's the mole to mole ratio. And then to finish this off, we're going to need to know the molar mass of the ammonia. I've calculated this in advance so I can do it pretty speedy. And so using that, we now have our calculation in grams of the ammonia. Oh, my 3 got really funky there. Okay, so you can always go back, like I keep saying, you can go back and do that crossing out, double check you've put all your unit factors in the right place and everything makes sense. If I calculated this all out, this comes to 60.8 grams of NH3. This is best case scenario, if you want to think of that. This is your theoretical yield. So best case scenario. Did I spell scenario right? Hope so. You can correct me. email me if I've spelled it wrong. So if I want to, this is now my theoretical yield. So my theoretical yield is that 60.8 grams of NH3. The percent yield would be what I actually got, so 55.6 grams out of a total possible of 60.8 grams times 100. And I didn't write the equation for that out just because I was a little jammed for space here, but that is at the top of the page. That's percent yield is actual yield over theoretical yield times 100. And so this is what your percent yield is. On your calculator, you can figure that out. Our percent yield is 91.5% yield. We made 91.5. We made 91.5% of the ammonia that we could have possibly made given the starting amount of that nitrogen gas. So let's do the last one here. We've gone through a little bit of the stoichiometry, the limiting reagents, and now the last topic is percent yield. And this question has it all. Luckily, we are starting with a balanced chemical equation, so we don't have to do that for ourselves. This one says that a student combines 50 grams of phosphoric acid with 50 grams of calcium hydroxide in a beaker. This is a neutralization reaction, a double displacement reaction. We're going to have to figure out the limiting reagent, and then after we know that, we want to calculate the theoretical mass of calcium phosphate produced, so that's over here. And then it says, but experimentally, if we only made 58.5 grams, what is the percent yield? So let's take a look at this one. We're going to have to figure out which one runs out first because we were given all this information. So we'd start with 50 grams of the phosphoric acid. The molar mass of phosphoric acid, maybe I'll just put that up here. You can take the time to calculate it. And we're also going to know the molar mass of the calcium hydroxide. Would have been really nice if this was one that had it all written out at the top. Or I guess that's what I'm doing for you now. So do your work and check your answers. And phosphoric acid. The last one that we're going to need, and I'm just going to jump the gun here while we're doing molar mass. This one takes forever. I did it in my notes. Okay. So now that we have all those molar masses, I think those are all the ones we're going to need. There's nothing about the water in here. So back to this phosphoric acid. We know that 1 mole of phosphoric acid is 97.994 grams. Oops, sorry. And so I'll calculate that on my calculator. I get 0.51023, blah, 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 blah. I'm going to divide by that coefficient to figure out how many reactions I can do. I'd get 0.255 reactions. Let's move on to the other thing here. So we know that we've got the 50 grams of the calcium hydroxide. I didn't write that out the front again there. I'll just make it consistent. You can write it out the front. Okay. So we need the molar mass of the calcium hydroxide. Oh, look, I already did it. 1 mole is 74.096 grams. I'll do that on my calculator. Leaving it in my calculator, I divide by the coefficient from my balanced chemical reaction because that tells me how many times I can run this reaction. It works out to 0.225. So this one, I always have a hard time with numbers that are flipped and stuff, but this number is smaller. That tells me that the calcium hydroxide is the limiter. And look, that's already one right there. Okay, so now that we know that, now we can move forward with calculating our theoretical yield because we're ultimately trying to figure out how much of this we can produce and then compare that to, oh, we didn't quite make that much. We made this much, that theoretical yield at the end. So we're going to start with our limiter and we're going to calculate theoretically how much of that calcium phosphate we can produce. So I know it's a little repetitive. Always converting to number of moles first, it seems. These are really long formulas too. And then we'd have to do that slide between our limiter and that product that we're talking about. So we're not talking about moles of calcium hydroxide anymore, hopefully. We are moving towards our product. We're moving towards the moles of calcium phosphate. So the numbers out front of those in the balanced chemical equation are a 1 and a 3. And so now that I have it in this, I have the last step to do, which is calculating how many grams of the calcium phosphate. Sorry for getting messy. Okay, and that number that I had calculated up top there was 310.8 grams per mole. So all of this is going to give me my theoretical yield. So I'll do all the math on this. I'd get 69.8 grams of calcium phosphate. This is my theoretical yield. That's my best case scenario, right? That's the maximum that I can produce. Now, nothing is perfectly pure in the lab. Nothing, like there's always contributing factors. In the lab for this chapter, you're actually going to have the real life reality where reactions are messy and they splatter all over the counter. So in this, we want to now consider what our percent yield is if we didn't get 69.8 grams, but we got 58.5 grams out of that possible perfect world scenario. This gives me a percent yield of 83.8%. Most of the time your percent yield, like test scores, is going to be less than perfect, or me making videos less than perfect. Sometimes you can end up with bigger than expected, and that's usually from impurities that are contaminating the product that you're making. So maybe it's another product that didn't boil out or something like that. So typically they're less than 100. If you get more than 100, it's kind of like with percent error, you know, it's still not 100%. And so, yeah, just keep that in mind. There's a lot built into calculating this theoretical yield, but understanding what to do with that for percent yield is the last step.